If you ever wonder why some applications slow down over time, why it crashes frequently, why seemingly simple programs consume a lot of RAM, then this is the episode for you. We will explore how memory management will work and the difference between automatic and manual memory management and the common pitfalls that can silently slow down the efficiency of your application. Welcome back to what every program should know about memory. Today we are diving deep into one of the most important topic in the software development, which is memory management. Whether you're working with the automatic garbage collection languages like Python or Java, or you're working with the manual memory management languages in C or C++, understanding how memory should be handled and should be managed is key to avoid any performance bottlenecks, security issues, and memory leaks. Before we are engaging ourselves to the concept of what is the automatic garbage collection is or manual management, let's think about the fundamental question here. What is the memory management? As we talked about in previous videos, every programs, when they need to store data or variables or data structure, it needs to store it in the memory. But memory is not unlimited. As you know about the pyramid shape from the memory hierarchy, how we handle this memory directly impact the speed, the latency, and the performance of our application. Think of a memory as a workplace where your program does its job. The more efficiently that your program uses this workplace, your application in general will be much smoother and also efficient. But if you mismanage memory, leaving clutter behind, taking up too much space, or failing to clean up unused data, you will fall into the serious problems. Now that we understand how crucial and how critical memory management is, let's talk about two primary ways that programming languages handle the memory: automatic garbage collection and manual memory management. Modern programming languages like Python, Java, C#, they have automatic garbage collection, which is responsible to automatically manage the memory. This helps the developers to allocate and deallocate the data automatically by the programming languages itself. So developers, they don't need to take care of freeing the memory when the data is allocated and the memory is unused. If we want to look deeper into the garbage collection, let's assume, for example, while your program is running, the objects are stored in the heap as we talked about it in the second video. Over time, these objects that you save into the heap, they are basically unused in your program and your program will not use them anymore. The garbage collector job is to identify this unused data and unused object and free the memory from it. Here is an example. Suppose we have a Python class like this. We create an object out of the class of example, then we assign none to the object. As soon as the garbage collector sees this assignment, it frees up the resources from this object. This happens automatically and you don't need to worry about it. Another example that we can show is from Java. The same example here shows that the object is created from class example, and after it's assigned as a null, the garbage collector will automatically free the memory from this allocation. At first, automatic garbage collector sounds a perfect solution. Why won't we want to use it for all the programs that we have to make everything fully automated? There are some downsides for the automatic garbage collectors, and these downsides can affect the performance of the system and performance of your application. The biggest issue with the garbage collectors is that they are not continuously running in your system. They are running in unpredictable times, often pausing your program when it's running while the garbage collector is scanning to find unused data which can be freed from your memory. This is known as a GC pause or garbage collector pause. For example, in Java, garbage collector can cause noticeable lag spikes in your program while your program needs real-time performance. Another downside of garbage collection is higher memory usage. Since objects are not freed immediately after they're unused, garbage collected programs requires more RAM usage compared to the manual memory management. So what about manual memory management languages like C and C++? In those languages, unlike the garbage collectors languages, developers need to free the resources after they don't want to use the data anymore. Here is an example how manual memory management works in C++. In this example, we assign the data into the heap. We print the value of the data to make sure that the data is there, and at the end we need to free the memory from the data that we defined at first. If you forget to delete that data from the memory, you will have the memory leak. Although manual memory management gives you the full control and full power over controlling everything in the memory management, it comes also with a significant risk. If you don't handle it properly, you can have dangling pointers, memory leaks, double free errors, and segmentation faults. If the memory is not properly managed in these languages, it can also cause security vulnerabilities. Now we understand how garbage collection works and how manual memory management works. Let's address a common problem that affects both, which is called memory fragmentation. This issue can silently degrade the performance of an application over the time when it's running, and if your aim is to design a high-performance application, this is essential to know. What is the memory fragmentation? If you plan to pack a suitcase for a trip, you want to be able to fit as many clothes as possible to your suitcase. If you put them in a tidy order in your suitcase, you can fit a lot of them. But if you put them randomly in your suitcase, there could be a waste of space in your suitcase, which stops you to add more clothes in your suitcase. Memory works the same way. Over time, your program allocates memory and deallocates the memory, which at the time it can cause some free gaps between this allocated and deallocated memory to appear between these used blocks. These gaps called fragmentation, and they make it hard for the large data to be allocated into the blocks. Fragmentation can have different types. External fragmentation, for example, occurs when free memory is scattered all over the heap, which prevents large allocation. Even though there is enough total free memory available to be allocated, it's not contiguous, so large data cannot fit. For example, if the programs allocate small and large data randomly into the memory, the gaps between those will not be used anymore because large data cannot be fit into it. So we can call it the gap is too small to be useful. Internal fragmentation occurs when allocated blocks are larger than needed, wasting space to each block. It happens because memory is often allocated as a fixed size allocation, even if the program needs portion of it. But how it can slow down your application? The first thing is that it can increase the memory usage of your application. For example, fragmented heap forces the operation system to allocate more memories than it's needed for your program. This wastes RAM and can cause swapping. When the RAM is full, then the storage will be allocated as a moving section for your data to be put on, which means that your program will slow down significantly. Another side effect is a slower memory allocation. Since memory fragmentation can cause non-contiguous memory blocks, it takes more time for your system to search for the large enough blocks in order to allocate your data into it. And this makes dynamic allocation like malloc or new slowing over the time. Memory fragmentation also can cause cache inefficiency. As we said in the second video, CPU works much more efficient when data is allocated sequentially. But when data is scattered over the memory, CPU cannot find it in a continuous manner. It means that the chance of cache misses are getting much higher than before. If I want to give the real world example, I can give you an example about the game engines. A game frequently loads and unloads textures, models, and assets into the memory. If the fragmentation builds up in the game, as a gamer, you will experience lags, stuttering, and also crashes, especially for the time when the game needs to allocate large object into the memory. That's a difference between high performance games and low performance games. There are several solutions that you can address in order to avoid this problem. As a first solution, you can use memory pool for frequent allocations. So instead of repeatedly allocate and free the memory, you can allocate a large pool of memory upfront and reuse it over the time in your program. This minimizes the fragmentation and improves the memory allocation speed. If you want to implement a simple memory pool in C++, we can have this example. In this class of the memory pool, we define the free blocks in order to allocate the data upfront for our class. In the constructor, we defined what is the chunk size that we want to have, what is the count of these blocks that we want to have. In the allocate function, we return the block that is already free from this pool of memory that we define at first. So if we want to deallocate it again, we push back the block into the free block. The next solution is allocating large objects early. So if we allocate large objects at the first of the program, we make sure that the fragmentation doesn't happen, since the allocation of these large objects happens into the contiguous memory blocks. Also, in programming languages like C++, we can use vector instead of dynamic array. In this example, the vector is already defined as a large object, which makes sure that memory allocation is contiguous. There is also defragmentation, like compacting the memory. In the garbage collector algorithms like mark compact, it automatically arranges the memory to reduce the fragmentation. In C++, however, you can define your custom memory allocators, leads to the less memory fragmentation. So fragmentation in general is a hidden enemy that you need to take care of because it can slow down your system over the time when it's running in different systems. You need to have a deep understanding of this memory allocation in order to implement memory pools or intelligent allocation strategies and defragmentation techniques, which makes your program more efficient and run much more smoother. So that's it for today. In the next episode, we dive deep into the pointers and why they're really important in the programming. So until the next episode, goodbye.